In this video, we're going to explore some of the key properties of the gradient vector, which is simply that package, gradient of f equals the x partial derivative of our function, comma the y derivative of our function at a particular point. What we're going to start with is determining the direction in which a surface has the largest possible positive slope. And if that is what we're looking for, then what we're talking about is a directional derivative, which is computed as the gradient of f dotted with the direction. So the idea now is we want to pick u to maximize the slope, that du f of ab part. Well, how can we go about doing that? Well, the dot product is what we would be computing to get a number, and that dot product is going to be equal to the gradient of f, its magnitude, times the magnitude of this u vector, times the cos of the angle between them. Now one of these is just 1. The vector u that specifies the direction we said earlier has to be unit length. This gradient vector, it's fixed. It's whatever the x derivative is and the y derivative is as a package. So fixed based on the point and the function f. And so the only thing that we can choose is the u vector, which modifies the angle theta. So if we choose different u directions, we're going to get different angles, and we're going to get different cosines of angles. So what should we pick to maximize this value? Well, to maximize our slope, which is our d up here, which is equal to all of this, we're going to need to maximize the cos of theta. And the way we maximize cos of theta is we choose theta equals 0. That is where the cosine graph has its peak. And that leads to a wonderful conclusion. To go uphill the quickest, or uphill in the steepest direction, and that is how we can interpret the largest positive slope on the surface. What we do is we go in the direction of the gradient. So we look at this formula here. We want to maximize the cos of the angle. Well, the angle it does that is 0, and that means u and f should be parallel. If we want to go uphill the fastest, or find the steepest uphill direction, we have to align the direction we're moving in with this gradient vector. We capture that in this next slide. Once we've computed the gradient of f, that direction is the direction of maximum increase of the function at the point AB, or that more geometric interpretation, the gradient at a point points in the direction of the steepest uphill slope. Let's explore that concept through a simple example. We have a plane, which is about as simple a function as we can get while still being interesting. When we choose a point on that plane, the point 1, 1 as our inputs, we can find the z value. It would be 1 plus 2 plus 3, it would be 6. But if we ask from that location, which direction should we move to move uphill the most quickly, we've just answered that question in the direction of the gradient vector. All right. Well, then we need to find the gradient vector, and that gradient vector is equal to the package of the x partial derivative, comma, the y partial derivative. Well, here we have our function. This is our f of xy. So we can compute those partial derivatives. We scan across. X is the variable for the x partial derivative, which is going to get 1. And fy is going to equal 2. So the gradient of f at any point xy, turns out to be nice and simple for this, is going to be 1, 2. All right. That is the direction we should move in. move in to go uphill the quickest. And there we are. All right. Can we confirm this? Absolutely. If we look at the contour diagram for the surface, we can see, looking at the heights, we have the peak over here. Well, there's no peak in a plane, but higher elevations over here, and going downhill in this direction. And we found that the gradient vector at any point was equal to the 1, 2 vector. Well, that's 1 over and 2 up. Hey, that is going to be up like this. And if we think about, this is a map representing a vertical view of a surface, and we can see the heights of the surface through the contour lines. Then if you asked, what direction should I travel in to go uphill the fastest? Or more explicitly, with the steepest slope. I know that all of these directions here are uphill, but if I want to go uphill with the steepest slope, I want to get to the next contour. I'm at height 6, I'd like to get to the next highest contour, height 8, as quickly as possible. Well, that is going to be this direction here, which was that vector 1, 2. So we get a perfect alignment between the direction we found by pure calculation and the direction we found with steepest slope using the contour diagram, getting me to the next highest contour in the least possible distance, because that's what would indicate the steepest slope. And that gives us a good visual confirmation that our analysis, based on the dot product that we did earlier, is valid and can be reflected in contour diagrams or graphical analysis of the surface as well.